Hello. What I plan to do this time is go through a typical exam question about Thevenin. It's quite commonly one of these questions in section B of the exam. This one you may recognise. It starts off with a basic bit of book work, just state Thevenin's theorem. And any reasonable statement of the theorem will do. It doesn't have to be word for word. The fact that there are 3 marks suggests that I'm looking for 3 things, and that is in fact true. The key things I'm looking for is that Thevenin's theorem applies to linear circuits. It applies to 2 terminal linear circuits. And it states that any 2-terminal linear circuit has an equivalent network which consists of a voltage source and a resistor in series. So, I'd be looking for something like this. Any 2-terminal linear, prefer to call them networks because they don't actually have to be circuits. Any 2-terminal linear network has an equivalent network which consists of a voltage source and resistor in series. You could draw a voltage source and a resistor in series. That would be nice, but not essential if you already said it in words. The way the marking scheme went, you could actually have just drawn that diagram, written the word linear, and written the word equivalent network, and that would have been enough to get you all 3 marks. But I would prefer a sentence that makes grammatical sense. Not many people had trouble with the first bit. Second bit, different story. Second bit was this one. Actually put that into practice, derive and sketch a Thevenin equivalent network for this particular network here. Now, this is a linear network. It has to be, otherwise it doesn't have a Thevenin equivalent. And any linear network like this can be analysed using superposition, and that's usually the simplest way to do it. You could do a nodal or mesh analysis on this if you wanted to, but it's probably easier and less risky to do it by superposition. Superposition, you may remember, the idea is you take each of the sources in turn, work out what the voltage across the output would be due to that source, and then just add up those 3 contributions to the output. And as long as the circuit is linear, that will give you the total voltage across the output. So, we'll start off just looking at the 6-volt source. The 6-volt source here, a 3K resistor, a 1K resistor there. Now, if the 3-volt source here is set to 0, it's effectively just a wire. A voltage source set to 0 is a wire. So that would just look like this. A current source set to 0 means there's no current flowing down from A to B through the current source at all. So we can just ignore it. The equivalent of this network here, when you're only considering the 6-volt source, is just this network here. Well, the voltage from B to A of this network, that is just a potential divider. And this output is going to be given by the standard potential divider formula. 6 volts times, in this case, 1K over 1K plus 3K, which is 6 volts over 4, which is 1.5 volts. And that's the first contribution to the voltage across the output here. Second contribution, just consider the 3-volt source. Now the 6-volt source is set to 0. So this is effectively a wire. The 3K resistor here is effectively connected right down there. I could draw this circuit and it would look like this. Well, that is also a potential divider. It's not quite as obviously a potential divider as this in. If you can't easily see this is a potential divider, you could just solve this by saying, right, we've got 3 volts between this point here and this point here, so we must have 3 volts across these 2 resistors in series. If we've got 3 volts across these 2 resistors, then the current flowing through these 2 resistors round this loop of the circuit here, the current must be 3 volts divided by 4K. And if that's the current flowing down through this resistor, the voltage across this 3K resistor, by Ohm's law, V is the current times the resistance, would just be 3 over 4K times 3K, which works out to be 9 over 4, or 2.25 volts. And that's the second contribution to the voltage between B and A. Third contribution is the contribution due to this 4 milliamp current source. So we have to do that one as well. You're earning marks for each one of these, by the way. Set the 4 milliamp source on and turn these 2 voltage sources to 0, replace them with 0 voltage sources, in other words pieces of wire, and what we'd end up with is this. And if you're not sure what you're doing, it's a good idea to actually draw out these component circuit diagrams as well. Right, now here we have a 4 milliamp current source which is sending 4 milliamps up through a parallel combination of a 3K and a 1K resistor. Well, if you put a 3K and a 1K resistor in parallel like this, then the equivalent resistance of those 2 resistances, we could work it out here, would be 3K times 1K divided by 3K plus 1K. Oops, that should be a K, not an I. 750 ohms. So we've got 4 milliamps flowing through what appears to be a 750 ohm resistor. And if we just apply Ohm's law to that, V equals IR again, we would end up with 4 milliamps times 750 ohms, volts. So the contributions to the voltage between A and B are 1.5 volts from the 6 volt source, 2.25 volts from the 3 volt source, and 3 volts from the 4 milliamp source, except have to be very careful about the directions. If I've got 4 milliamps going through the resistors that way, remember that current always flows through a resistor from the high voltage side to the low voltage side. So if there's 3 volts across these 2 resistors, but the current is going that way because it's flowing around the circuit like this, then this point here must be 3 volts above this point here. In other words, B is above A, due to the contribution from this 4 milliamp source. So the voltage from B to A in this case, because B is above A, going from B to A is actually going to be negative. We're going down in voltage, following the current down in voltage through the resistors. So this is actually minus 3 volts. If we go from B to A, we are dropping by 3 volts. In the other 2 cases, we were going up. So the total voltage from B to A is 1.5 volts due to the 6 volt source, plus 2.25 volts due to the 3 volt source, minus 3 volts due to the 4 milliamp current source. Add up all of those. 0.75, 750 millivolts. And that would be the open circuit voltage. The voltage between B and A when there is nothing connected to B and A, nothing outside here. Now the Thevenin voltage is equal to the open circuit voltage, so we have just calculated the voltage of the voltage source in the Thevenin equivalent circuit. The only thing left to do is work out the resistance, the Thevenin resistance in the circuit. And the easiest way to do that is just to consider the circuit and set all of the independent sources here to 0. If I do that, then the circuit that I've actually got is like this. Setting all the sources to 0, all I'm left with is a 3K resistor in parallel with a 1K resistor. And looking in from the outside world, with all the sources turned to 0, I would just see a 3K in parallel with a 1K. I've already worked that out here. That means that the resistance is 750 ohms. So my Thevenin equivalent circuit should look like this. That'll do. Probably the thing most likely to trip you up is that the voltage due to the current source is in the opposite direction to the voltage due to the 3 volt and 6 volt voltage sources. You need to make sure that you get those the right way around. You don't lose that many marks if you didn't get that bit, but you know, every mark counts. It's a good idea to get it right if you can. Okay, that is section B. 6 marks for getting all that right.